Alright, we just got done talking about centripetal acceleration. Well, now we need to talk about the next step, and that is the cause of this motion. Centripetal acceleration isn't the cause, it's more of an effect. If, as I read the screen to you, if AC, centripetal acceleration, is an acceleration towards the center of a circular path, what would the force that causes the circular motion be called? If it's centripetal acceleration, what do you suppose we call it? Any ideas out there? How about centripetal force? Centripetal force seems like a very good answer. If you got centripetal acceleration, it'd be centripetal force. If the acceleration is towards the middle, what direction would the force be? And I spilled the cookies too quickly there. Towards the center seems like a very good answer here. It's always to the center. The acceleration to the center, therefore the force is also directed to the center. Just kind of goes along with what we learned way back with Newton's laws. Looking at equations, if we have this equation right here, if centripetal acceleration is equal to tangential velocity squared over the radius, well, looking at forces, and I reference Newton's second law again here, force equals mass times acceleration, right? So centripetal force is equal to mass times centripetal acceleration. Therefore, centripetal force is equal to mass times Vt squared over r. So you just substitute that in for there. So jot that down. That's kind of important. Things to think about while you write that down on test questions. The idea that the tangential velocity and the centripetal force, and therefore centripetal acceleration, are perpendicular to one another is kind of a big deal. You want to pay attention to that little factoid, that little data piece, that the tangential velocity is in one direction that is perpendicular to the centripetal force, centripetal acceleration. That's what causes it to go in a circle. All right, ready to move forward? Here we go. Now, when we talk about centripetal force, we're not just going to be talking about planets. We're going to be talking about earthly things, things that you've experienced in your life. And we're going to talk about not just centripetal force, but we're going to talk about this other imaginary force called centrifugal. And I'm going to type one right now, and if you ever say this word on a test, you will receive 0 credit for the entire question, because it is one of those things that people say that's wrong. Yeah. People, oh, I spelled it wrong. People say that word, well, they're wrong. Makes them look really ignorant when they say that word. That does not exist. Don't ever say it. Don't write it on a test. You'll receive 0. That's fake, not a real word. The two words that we do use is centrifugal force and centripetal force. These two are legitimate. Oops. These two are legitimate terms. Centrifugal and centripetal. This one's outward. This one's inward. While this one may be a false, not in real force, but still, this is a legit topic. The other word I had, not a real topic. Don't even bring it up. Pet peeve kind of thing. All right, now let's look at some amusement park rides, because these are very good for centripetal force. Amusement park rides utilize centripetal force to make themselves thrilling. If you just had a ride that was just straight in a row, the only way it'd be fun is if it was really fast. You know, Top Thrill Dragster being the idea that you go 120 miles an hour. That's fun. Other than that, every other ride in the park utilizes spinning and curving, and they're utilizing inertia and centripetal force. So let's look at the Ferris wheel here. As the Ferris wheel rotates, right? As it rotates, we want to analyze a couple things. Number one, what direction are the forces going, and in what direction gravity is going. So, As it's spinning, and to make this, a real Ferris wheel is kind of boring. You don't really feel a lot of things when you're on a Ferris wheel. And where you are in relationship to the ground, are you heading towards it, away from it, even with it? Okay. To the side, remember, we're doing this in a fast spinning ride. We're just looking at one thing at a time. Now, centripetal forces to the side, force of gravity is downward. In reality, the differences that you feel during this kind of ride are much more minimalized. We'll rotate it more towards the bottom. Now here we're feeling something again. You very much feel it in your guts. If your head is oriented upright, you're feeling your stomach pushing down through your pants. Out to the side, again, the sensations are not large. The feelings just aren't that different here. Then you get back up to the top. I remember I had an argument with my sister about this. She liked to ride Ocean Motion, and we were standing in line arguing about the legitimacy of, why this actually works the way it does. And my cousin, who's an engineer, was standing with me, and he didn't back me up, and I was kind of frustrated. The reason that you feel on Ocean Motion, you feel things in two places. Number one, at the peak of the swing, and number two, at the bottom of the swing. And the difference is very much greater. You definitely feel like your stomach's trying to go through the seat of your pants at the bottom. You don't feel it nearly as much. You feel a little bit of a flutter at the top, and that is because with Ocean Motion, if you recall, it's like a swing of a pendulum. At the top, your inertia is totally changing directions. Your momentum is changing directions there. But at the bottom, that's what we're talking about at the bottom here. And all of a sudden, your inertia is really have a lot to do with what you're feeling. Your inertia and gravity, and your inertia gives you this centrifugal force that I was talking about. And centrifugal force here is kind of directed upward and outward, because that's where your inertia is heading. Down here at the bottom, your inertia is heading sort of downward and forward. And that feeling of your inertia is where your stomach feels like it's up in your throat, up at the top, or down in the seat of your pants at the bottom. That's where you experience your inertia and where you experience centripetal force and centrifugal force. Well, let's make another comparison. Let's talk about a hill, or a hill on a roller coaster, or a hilly road in a car. Okay? As you crest a hill like this, your inertia is pointing up and out over the hill. That's why it feels like you're coming out of your seat. And in some rides, you are literally coming out of your seat. Just ride the Blue Streak. Take your life in your own hands there. It feels like you're coming up out of your seat because that's where your inertia is going. It's going up this direction. And the reason it feels more extreme than other ways is because there's also centripetal force happening. So you got a curving inward force towards the center of the radius here of the hill. That's one force you're feeling, and then you get this other force that's heading out that way, and that's makes you feel funny. And then down at the bottom, now your inertia is kind of coming down like this out of the hill, but then you're going back that way, and it feels like you're being separated from the squishy inner parts of you. Now let's talk about this other thing. You're driving your car, and you come up to a curve. And so Bob's in his car, he's on a curve, his sunglasses are on the dashboard. As it goes around this curve, what will happen to his sunglasses? So you got aerial view, you got Bob, dashboard, sunglasses. As he comes up, what's going to happen to the sunglasses? Are they going to go towards him, or are they going to go away from him? Give yourself a second to think out an idea on that. Got one? Okay. The inertia of the sunglasses is forward. The car is going to go a different direction. The car is going to curve off to the left here. Therefore, it's going to feel like the sunglasses, from Bob's perspective, are going to begin to slide sideways. In reality, they are following the inertia of the car. The inertia of the car keeps changing, though. Or, the inertial direction of the car keeps changing. Inertia wants them to go forward while the car moves out from under them. Okay, that's why your glasses slide around. Or, like in, I believe it was Tommy Boy, when they're driving down the road in the car, and he puts candy on the dash, and Chris Farley puts candy on the dashboard in David Spade's car, and the candy rolls across the dashboard and down into the heater. That was because of inertia. Okay, centripetal force, centrifugal forces. If he wanted the sunglasses to slide towards him, he'd have to go around a right curve instead of a left curve. And then it would slide towards him because then inertia would be pointing that direction. When I get back, I have a few videos for you on fighter pilots and G-forces, and we'll talk about that in distinct detail together. But let's do this here. Now we got this airplane, and this airplane's doing a stunt. Okay? Goes around in a loop-de-loop, very pathetic loop-de-loop, but still we want to find the centripetal force on it. So to do that, Vt squared over r, right? So Vt, so squared, okay, get two of them, times m, because I didn't say that out loud, times m over r, right? So get out your handy-dandy calculator so you can calculate this. By my reckoning, let's see, 30 times 30, that seems to me to be about 900. And then I'm going to multiply that by times 70.5. And the sample problem is from the sample problem book. It's probably a model airplane. And I'm going to divide that by 100. And I'm going to get a centripetal force of 634.5 newtons, if you can read that calculator there. Okay, that's it, guys. It's not crazy calculations. Don't forget to square the tangential velocity. So if I just maybe dump some paint here. That didn't show up as well. That's much better. Homework 228, 1 through 4. Good luck.